In this exercise, we will learn how to solve regression tasks using Scikit-Learn. For this purpose, we will look into the data of our previous competition, which was organized 1.5 years ago, where the target was to estimate head pose angles. In this case, the data consisted of images of people who were looking at different directions in front of the camera. And the direction was described using two angles, the horizontal angle of the view and the vertical angle of the view. The data can be downloaded from this website, which is given in the assignment text. So essentially what's inside of this website is first of all a paper that we have written about the competition. You may look into it if you want more information about the background. And the data can be downloaded from this link. And this data file contains altogether 4 data files. These are the training features and corresponding test features for the secret test data of that competition, and then the target labels. And if we take a brief look at what's inside of each one of these files, here is first the contents of the X-train, the training features. In this case, what I have in here, the first row is just the header row, and then on each row at first I have the index of that row, 1, 2, 3, just a running number. And then I have almost 2000 features at each row. In this case, the features are called dense hog features that you can compute in MATLAB using the VLFit toolbox, or alternatively there's also a hog computation possibility for Python based platforms as well. However, the dense hog features that were used in the competition are readily available and computed for you, so you don't need to worry about that. Based on the features themselves, your task is to predict the 2 angles. For the training data, the angles are given in Y-train file, and similarly to the features, in each row there is the index of the sample and then the 2 target values. In this case, I would like to predict that the horizontal angle was -15 degrees and that the vertical angle is -45 degrees. In addition to the training features and test features together with the training labels, there is also the 4th file, which was secret at the competition time when it was running, but has now been published. It contains essentially the same data as Y-train, but in addition to that there is a 4th column in addition, which specifies the split of the secret test data into public leaderboard and private leaderboard. Similarly, like you have right now in the ongoing competition, the public leaderboard is available, is shown all the time, while the private leaderboard will be revealed after the competition ends. Now in this exercise we will use the complete secret data. So we don't care about the split into public and private. We use all of it. Additionally, there is a ridge regression template for training a ridge regression model using MATLAB. Of course, in this exercise we will concentrate on Python instead. So what to do? The task consists of 2 parts. The first part is to train a ridge regression model, and the second part is to train a classifier that we will use for this purpose. Namely, now that the target values are integers, you can treat it equally well as a regression problem where you try to predict this number, or you can find out which are the possible labels, because there are not all possible integers in here, only quite quantized set of angles that are available in the data. So you can treat this as a classification problem instead, where -15 would be one label of your classification problem. 0 would be another label of your classification problem. This is yet another label, and altogether there are about 15 different labels for both angles, so it can be treated as a classification problem equally well. we are doing both in this exercise. For the regression template, you will gain 2 points once you have solved it. For the classification version, you will gain another 2 points for your exercise score sheet. So that will raise your percentage from 70 to 80, roughly, a bit more. So it will give you actually 1 point for the exam if you are able to solve both. The first one is ridge regression, which is maybe more straightforward approach. We will try to predict real valued outputs representing the angles. First, we load the data. In here, we use numbus load text function, and we need to specify that the header row will be skipped and that the delimiter is a comma instead of the default semicolon. Then, similarly, y train x test, and then the y scoring, which is the scoring the secret test data labels, contains one additional attribute, which is use calls where I specify that I only want to extract column 0, 1 and 2, because the last column with index 3 contains the public private attribute, which I'm not interested in at all. Also in here I throw away the first column of my features because that was the running index. Then I train a ridge regression. It is quite similar to the regularized logistic regression classifiers that we looked into, and also has a regularization parameter. This tells how strong the regularization is and how much freedom there is in designing the coefficients. In here I'm specifying a range which is from 10 power minus 4 until 10 power 4.5. And I'm collecting the errors for each alpha into this list. Now for each alpha, I initialize the error for this alpha to be equal to 0, and I train two models. I train the models in the for loop because I need to train a separate model for the horizontal angle and for the vertical angle. I do it in a for loop for the two columns. What is missing from here, what is for you to write, is that you define a ridge regressor first and you specify the regularization parameter alpha, which is this one. And just look at the help of ridge function at Scikit-Learn to find out how to do that. It is quite straightforward. Then you fit like any other Scikit-Learn model, except that the target values are now extracted from the column 1 or column 2 of my training data. And then what you do is predict. You predict using the X test. And then you will get the prediction for the particular column of your test data. And let's say it will go in here. So after that we can compute the error for our experiment. And the error in this competition was the sum of absolute errors or absolute prediction errors. This is what we predicted, and this is what the real angle was for the particular column. Finally, we need to scale the errors or average the errors over the number of angles altogether in the two columns. So because I have this many samples, and for each sample I have two columns, I divide the errors by the number of angles that I have predicted overall. In here I'm just reporting what was the accuracy or the prediction error for each alpha, and then finally I plot the result in a nice figure which looks like this. You should finalize your experiment with a plot that looks something like this. In here is the regularization parameter, this is the prediction error, and the minimum is somewhere below 10, which is quite similar to what you can see at the leaderboard of the competition, if you look at that. So this is the first part, 2 exercise points for completing this. Then the second part consists of a classification approach for the same problem. It turned out that all the best teams in this competition used classification approach, although the outputs can be considered as real valued numbers. However, classification seemed to be more successful in this case, so let's look how that can be implemented. The key to implement that as a classification problem is this label encoder pre-processing module. The beginning of this template is pretty much the same as in the previous template. We go through 2 columns. We extract our target slightly differently to its own vector at this point. It's just the first or second column of my target. But what's different in here is that I encode the labels. If you look at the help of label encoder at Scikit-Learn, it simply transforms all the unique items that it can find from the target vector into labels 0, 1, 2, and 3, and so on. So it sort of compacts all the values that are in here into integers starting from 0. And in principle, the labels that I'm giving to my encoder can be anything. They can be string valued or whatever is unique for unique set of labels that can be found from the target. In this case, it's a bit simpler because the targets are now integer numbers. So it is just looking at which angles there exists at this column, and then it gives a specific label for each one. In here, it learns the labels, or just looks up at all the labels that are in the target, and in here they are transformed into integers starting from 0. It could be that -15 angle will be 0, labeled as 0, -13 will be labeled as 1, and so on and so forth. And then the same logic, train, predict, as usual, as we have learned so many times in the exercises. And the final step is slightly different. We need to do the inverse of what we did in here. In here we transformed the angles into labels 0, 1, 2, and 3, and in here we have to do the inverse. Our prediction gives us labels, not angles. So we need to transform the labels into angles in order to be able to compute the error. Take a look at the help of label encoder. There's a great example which probably clarifies the issue. And as the result of applying the inverse transform for the predicted labels for secret test data, you will get this prediction vector, and the error is computed exactly like in the previous exercise. Then we see how good the result is, and in this exercise the classifier will be random forest classifier, which is relatively good. Use use 100 trees for the prediction, which seems to give at least better result than the regression based approach. Of course, if you have time, you can increase it to 1000. Of course, if you have time and interest, you can try some other classifiers, because it's just changing one line of code in here in the definition of the classifier. But it will be enough to gain the 2 points. It will be enough to train this with random forest classifier and report what you have done. So as a final note, what you should return is a PDF file where you describe what you have done, where you include also this plot. You can easily save the plots from the save button in whichever format you wish, and then just include everything into Word or LaTeX file, compile it into PDF, describe briefly what you have done, and attach as an attachment all of the code that you have created. Return that by the specified deadline, and the points will be added to your score sheet, and they will help you in getting a better grade or fulfill the 60% limit, which is the minimum. Thank you for your attention.